particular, I talked about how an open quantum system, which is interacting with its environment, we should express the system's evolution in terms of the reduced density matrix. So the So I had said that, you know, if the system, so here's the system, here's the reservoir R, and the system reservoir together, the total density matrix, let's say that's in a pure state, this psi, and then I expanded it out in terms of the system and reservoir basis, right? So any state psi can be expressed like this, and then I wrote down an expression for the reduced density matrix, because as I said, any expectation S, which is written as psi S psi, can be written in terms of just the pure system operators or system basis. So this part here I was calling as the density matrix rho S, which is the trace over the reservoir of the full density matrix. Okay? And that is obtained by taking the sum over all the reservoir degrees of freedom and the full density matrix psi psi. This is the partial trace, okay, which is represented by this trace over reservoir degrees of freedom. And I quickly tried to give an example, which I didn't have in my notes. I thought I would just come up with it, something that I had seen a long time ago, and I kind of screwed it up. So let's go back to that. So imagine that the system is indeed in this sort of state, 1 over root 2 plus 1 over root 2, which is a superposition of 0 R0 and 1 R1. Okay, and this is a pure state. In fact, it's an entangled state between the system and the reservoir, right? And then we could calculate the density matrix psi psi for this system. In fact, I wrote the density matrix correctly. And the basis in which we had written this is, in fact, the right basis, where we increment the R1 and R0 variables successively, and then the first qubits variables successively. So, as you can see, initially I wrote it as 0 R0, 0 R1, 1 R0, 1 R1. Okay? And the reason for this is, when you write it in this basis, now if I want to make a reduced density matrix for purely the system part, I will take the trace over the reservoir degrees of freedom for the full density matrix rho SR, which is over here. This is rho SR, right? The system and the reservoir are the total density matrix. And to do that, I should write this as a sum over the R0 and the R1. And of course, this matrix is going to be a 2 by 2 matrix, because that is for just the system alone. And in fact, if you stare at this long enough, you see, in fact, this matrix divides up nicely into subblocks, and wherever there's R0, right here, that's this first term over here, and R1 is this first term, that has the rho 0, 0 element right there. Okay? So rho 0, 0 is simply the trace of this matrix, which is half. Okay, of that block matrix. Rho, and of course up here is the same thing. Rho 0, 0. Careful. Similarly, you can see from that guy, rho 0, 1 is going to be 0, right? Because the trace of this matrix is 0 plus 0, and so on and so forth, and you get, in fact, the reduced density matrix half, 0, 0, half. Okay? So this hopefully answers your question to some extent. I mean, I think I had this right, except that I traced out the first variable instead of the second one. That was my mistake. And the second issue is I try to think about how I might do this in more general for more than 2 qubits. Like, for example, if you had like 3 qubits, right? Then how are you going to do this? Can you use some kind of dot product between the basis vectors R0 and R1 as written in this way? It turns out you can't. Okay, so there's no general way to do this. The things that I have learned so far are either you just do it in this way. You write out the matrix like this, and you write it in the right order. And then if you want to trace out, say, the last one, the last variable, say R0, then you write it in this way so that the last qubit is incrementing. And then you can just divide it up into these sub-blocks and take the partial traces of each of these sub-blocks. If you want to do any of the other qubits, say the first one, suppose you wanted to take partial trace over the first qubit, this system doesn't work, right? You'll have to like find, like I was doing last time, these guys, or what people do is they change the order of the basis label, okay? So they just simply put the one R0 up here, okay, and interchange like that, and they then can go back to doing the same partial trace like this. And in the most general way, it seems like people either use like a tensor, like a multi-dimensional matrix. So if you want to like actually do like say 5 qubit and find partial trace over 1, it's obviously it's easier to think about another dimension and to start to like go in that direction. And and of course finally the answer to all this when I ask some experts is there are computer codes already out there to take these kind of partial traces. So that seems to be the answer. If you want to go to higher dimensions, just use the code. Okay, which seems like a little bit of a cop out, but I guess that's how it works. But at least you can see for like 2 qubits how to do this, and as I said, by interchanging the qubits, you can take partial trace over different qubits and do it by hand. But then beyond that, it's a little bit becomes more complicated. Okay, so coming back now to this system. What I've given you, the handout is where we stopped last time, which is, and I did for you, of course, the example of a classical noise model, where I took into account, like, if, so here we introduce basically just this trace over the environment, and it turns out that when we take this trace over the environment and we want to find an equation purely for rho s, right? So all we care about is how the system evolves. We don't want to keep track of what is happening in the environment, okay? Lots of things might be going on. We don't want to keep track of all that. We care about our system, our qubit, whatever it is that we really are interested in. And to find that equation of motion for the system, we need to know some properties of the environment. That's what I introduced to you last time, which is one of the properties is the 2-time correlation function that comes out in a very simple classical model, where we took a Hamiltonian. So I'll erase this, since this was sort of meant to be an aside, which I got, kind of sidetracked into, but it was good. I think it helps you to see how the real examples work. Oh, and I should obviously point out here, you started in a pure state, which is an entangled state, 0R0 plus 1R1.
Sorry, I can't search the web with Apple Watch.
Okay. But the reduced density matrix that you ended up with had no coherence. Okay, this is a purely diagonal matrix. So this is one of the key features of entanglement. In fact, as we'll see later on, that even though the system, the joint density or the joint the density matrix for the entire system has coherences because it has off diagonal elements, but the reduced density matrix, which is the density matrix taken by tracing out the other qubit, has no coherence in it. So all of the sort of quantum information in this density matrix resides in the joint probabilities or the joint correlations, and there's nothing in each individual qubit. Each individual qubit looks like it's in some probability distribution, has no superposition state, right? If you looked at this density matrix, you would say that this qubit was not in a superposition state. And in fact, as we'll show, you cannot write any entangled state ever as the product of two pure quantum states. That is in fact the definition of entanglement, when you cannot do that. Okay, but coming back to our point here, that is that when we are considering the evolution of a system which is interacting with an environment, so now the Hamiltonian for the system was Hs plus Hr plus Hsr. Okay, so this is exactly what it means or implies by the subscripts. This guy is just purely the system operators. You know, for example, the example we did in the last class was even simpler than this. Was we had some h bar omega times sz for a spin plus h bar f of t sz. So you would call this hs and this is hsr, except that in fact we don't even have hr in this example that we did. That example was a purely classical example where the system has no back action on the environment, as we like to call it. Back action is just a way of saying that the environment does not get affected by the evolution of the spin. Okay? So in this case, for example, this one has reservoir evolution or operators, and this is of course the coupling. And in the last class I showed you for the simple classical example where there is no quantum evolution of the reservoir is not in any quantum state. We simply have a spin that is coupled to some noise stutter, which is a very normal example in most systems, right? You have your atom or your qubit which is sitting in your experimental setup, and it is always subjected to some kind of disturbance from the environment. Some power lines are fluctuating, some magnetic field is fluctuating, there are radio towers and TV towers, and all these things are going to affect the evolution of your spin qubit, for example, by maybe changing the local energy of the qubit, right? Because that's what this does, right? When you have an SZ term in the Hamiltonian, it affects the energy of the qubit. You could draw a picture, you have the 0 and the 1 state, or up and down state for the spin, and normally the splitting is h bar omega, okay, in this example. And instead I am saying that there is an additional fluctuation that is affecting this energy of the system. That was the example we did in the last class. And I showed you how as a very natural way, when you consider the evolution of this system using the unitary time development operator, you automatically get things like the 2-time correlation function for this f of t, and from this 2-time correlation function we could already draw some nice intuitive behavior of this system. For example, we saw at short times, or for example when the time is short compared to the correlation time of the system, then there is memory in the reservoir, in the classical noise, and that means that the decay of the system goes as a Gaussian decay, like it goes as e to the minus t squared, right? And when the evolution of the system becomes long compared to the correlation time of this noise, f of t, then the decay becomes exponential and we recover what we call the Markovian regime, where we no longer have any memory of the system. And what is the one thing I said that you have to remember about this coherence? Meaning, when is it that we can actually use techniques like spin echo to recover the original quantum phase or the original quantum information that we have put into the system? In which regime will I be able to recover the original quantum information or the quantum phase of the system. Let's say I started in the state psi equals say 0 plus 1. Okay, now it evolves over time, right? With time t, this is going to have, let's say, in this behavior, e to the minus I phi 1 over root 2, right? That's what will happen with this Hamiltonian. Neglecting all the omega parts and stuff. Like, of course, there is evolution at frequency omega, but I'm ignoring that part and just considering the part due to the external perturbation f of t. We saw that this guy is going to become like a decay, right? It's going to go as e to the minus t squared when the phase evolution essentially is due to the time, when the time is very short compared to the coherence time. Okay? And when the time is much larger than the coherence time, this guy goes to an exponential. Okay? So that's what happens to our system. And when we are in this Gaussian part, which means that there is memory in the system, that is that the phase phi that was imprinted by the external perturbation, right, can be recovered from the original system by applying a certain kind of pulse sequence. What is that pulse sequence called? Do you remember this? Ramsey would be just applying a pi over 2 and then another pi over 2, right?
Yeah.
But if you cannot undo the action of the environment, if the environment is random, then every time you run the experiment, you get some random phase phi, and over time you will get this sort of decay with t squared. That is indeed the Ramsey fringe. Okay. So imagine like you can measure in the logical basis 0 or 1. So this is okay. So you started with the system in the state 0. You applied a pi over 2 pulse. Okay, and then you wait some time t, and during that time t there is a phase phi that is accumulated. Okay, and then to measure in the 0 or 1 basis, you will again apply a pi over 2 pulse, and that way you will get either 0 or 1. If everything was perfect, you should recover back. Either you should go from 0 to 1, for example, right? If the phase was exactly perfect each time. But unfortunately, the phase is random, as I just said. And so what happens is, because the phase is random, when you average over many of these measurements, right, which you have to do in quantum mechanics, you get the probability to be in the state 0, you get a Gaussian decay of your probability to be in the state 0 as time increases. Okay? But as long as this time is shorter than the coherence time of the correlation time of the environment, you can actually fix this problem. How? Sorry? Apply a pi pulse in. So if you don't remember this, you should go back to our notes from last time, right? So if I apply a pi pulse, in between here, I switch the 0 and 1 states. I'm treating this in a different language than you might have seen in the last class. Okay? You can think of this as switching the behavior of the 1 and 0 states with some minus signs and so on. Okay? Because that's what the pi pulse does, right? It kind of like flips the 1 and 0. And now when I evolve again, I get e to the minus I phi over here plus e to the minus I phi over here. And now I can factor out the e to the minus I phi and I recover the original state, 1 plus 0. Okay? The reason I can do this is because I'm assuming these phases are the same in both evolution times, t. I'll let it evolve again over time t. And of course that phase will only be the same in both the halves of the spin echo sequence, as this is called, or Hahn echo. It will be the same in both halves of the Hahn echo sequence, only if the phase has not changed, which means that the system has some memory or rather the environment has some memory of what its original state was. That is that the correlation time tau c is longer than the evolution time t. You can also see this in the picture that I drew last time. So this is one way to think about it. Another way to think about it is geometrical, right? So instead of looking at the full Bloch sphere picture, it's often just useful to think about it in the xy plane, because oftentimes that's what we care about for the system. So in the xy plane, I start, let's say, with the system along the x-axis, right? That's the 0 plus 1 state over here. 0 plus 1 is along the x-axis. Then I accumulate some phase phi, okay, which causes it to evolve to another state over here, okay. And if I repeated the experiment many times, okay, which is what you do in a Ramsey fringe, then each time this phi will be some random variable, and you'll get some spread delta phi in the vectors, right? So you'll get some spread in those vectors. And in fact, what I've shown you is that the spread goes as a function of t squared, the time of evolution. It becomes basically like a Gaussian decay. The width of this distribution grows as like some Gaussian distribution. Okay, and what we are saying with the spin echo is, now if I apply another pi pulse, then instead of accumulating, first it accumulates this phase phi, then I apply the pi pulse, it flips the vector over around the x-axis, right? And now when it wants to again accumulate in the same motion, the phi, it will come back to the original state that you started with. Okay, so this is the idea of the spin echo. And this only, again, as I want to emphasize, again, is made possible only when the environment has a correlation time which is longer than the time evolution t in the sequence. Okay. So if you start with environments which are very, very noisy, where they have correlation time that's very short, then spin echo does not work. Okay. The correlation time of the environment has to be long compared to the evolution time of the system. Okay. So I'm going to stop talking about that part, because that was from the last class. It meant to be a quick review, and now I want to talk about what happens in the full density matrix situation when we have a full quantum evolution. Okay, and that's what the handout that you have basically outlines all of the mathematical steps. So this the example was for the classical situation where the reservoir in this case has no evolution of its own. The HR is missing because it's a classical reservoir, and we don't ever worry about what happens to the reservoir as a function of time, because it is not evolving. It's basically a classical system that's unaffected by the behavior of the quantum system. But now I want to take what happens when the system is coupled like this with the system operator, the reservoir operator, and the coupling. And to do that, so what I'm going to do on the board is basically just outline the major steps on the approximations, and a lot of the math is explained in the handout that you have with you. So the first step is to move into the interaction picture. So we apply, because if we did not have the bilinear coupling, then the system and the reservoir will evolve as normal, right? So for example, if you have an atom which is coupled to the electromagnetic field, then the atom will evolve according to its system operator, the reservoir will evolve according to its reservoir operator, and the dynamics is completely uninteresting. Okay, we know exactly what will happen. So let's get rid of those evolutions by applying the unitary operator HR plus HS times T divided by H bar, which will give me a new state vector, which I denote by psi tilde. Okay, this is in the interaction picture. The interaction picture state ket, which is given by taking psi and applying the unitary operator u that I just defined over here, and now of course we are interested in the density matrix, rho tilde, okay? The rho tilde is going to go as U rho U inverse, okay? And we can also define now the interaction picture Hamiltonian for the coupling, which will go as U HSR U inverse, okay? So this interaction picture density matrix and the interaction picture Hamiltonian for the coupling, we end up with the equation of motion for the density matrix, which involves only the interaction term or the coupling term and the density matrix for the entire system, the system and the reservoir, I guess. Okay, so that's it, right? That's what will happen when you substitute all that. And formally, we can integrate this. We can just say rho tilde of t is equal to rho tilde of 0 plus 1 over IH bar And when we see this kind of formal integration, we put this back in here and we want to find out what happens to the system's density matrix. Okay? The density matrix of the system now, remember we want to take the trace over all the reservoir variables, and that is what is given in your notes. I'll just write down the answer, that it goes as is going to be governed by the two-time correlation function of the reservoir operators. So substituting back this guy into here and taking the trace over the density matrix or the trace over the reservoir, I get an equation that is purely in the system variable, trace over reservoir of and of course we can keep going to higher order, but we're going to stop over here. That's a double commutator, and we can already see that it is going to have these two-time correlation functions in it once again. So this is where, so far this expression is exact, and we can keep going to higher and higher order, right? But usually we'll truncate at this order of the expansion, and we will look at some approximations that allow us to understand the nature of the system and reservoir interaction or the coupling. Because remember, we care about the evolution only of the system variables. So we'll start by the main assumption that the system and the reservoir are in a product state at time t equal to 0. Or rather, that they are unentangled at time t equal to 0. So rho tilde of 0 is rho s tilde of 0 times rho r tilde of 0. So there's no entanglement between the system and the reservoir at time t equal to 0. All of the entanglement comes about through the interaction term HSR. Okay? The next approximation, which is called the Bond Approximation, is similar to the earlier approximation that we had made, where we did not include the system, the reservoir variables. But now we're going to say that at some time t, okay, the system will factor, the entire system, I mean the universe, so to speak, will factor into a product of the reservoir at time 0 and the system at time T. That is, that the coupling term, although it has a big effect on the system variables, has very little effect on the reservoir variables. And of course, if the reservoir is large, like some electromagnetic field in vacuum, of course, vacuum is essentially extremely large. It has lots of modes in it. So the effect on the density matrix of the reservoir, if you think about the reservoir being the electromagnetic field in equilibrium, in thermal equilibrium with the walls or whatever, then the system as such is a small quantum system, has very little effect on the reservoir. The reservoir stays in its original state, rho r of 0, or you can equivalently say the reservoir is always in equilibrium. It doesn't change due to the system. Okay? The next approximation that we make is called the Markov Approximation. I've already explained it to you, which is that we are assuming that the reservoir correlation times are very short. Okay? So these are the big approximations that we make when we obtain the master equation for the system, and in fact it is carried out in the so-called Bond Markov Approximation. So the Markov Approximation is the reservoir has no memory. Its correlation time for the reservoir is extremely short. It is equivalent to correlation time short, or is a delta function. Compared to the time of evolution of the system, that is, that the correlation time of the environment is extremely short. Remember, this works well only because we are in this interaction picture where the evolution is purely governed by HSR, the coupling between the system and the environment. If you were to think about the original dynamics of the system, you might have some, say, atomic transition, which is, say, in the terahertz regime or hundreds of terahertz regime, right, if it's an optical transition. And you might have some electromagnetic field whose frequencies are also in the similarly hundreds of terahertz regime. So then you would say, oh, wait a minute, the system and the reservoir are both evolving very, very fast, and we can't always neglect any memory that might be in the system. This works well when we are in this picture where the reservoir and the system interaction, reservoir and system dynamics is purely uninteresting like that, where it's just purely the evolution due to the bare Hamiltonians, which we have taken out in the interaction picture. So in the interaction picture, what matters is the coupling, the speed with which the system and the reservoir are getting entangled is governed by this coupling term HSR of T, and this term is small, or the frequency with which it changes the system is small compared to the bandwidth of the reservoir. So the bandwidth of the reservoir is extremely large, and the coupling between the system and the reservoir is small compared to that bandwidth, so that the bandwidth of the system means if the system has large bandwidth, its correlation time is extremely short. You can think of it that way. There is a Fourier transform relationship between correlation time and system bandwidth, for example. Okay? Yeah.
That's a very dumb question. So
no, there are no dumb questions.
Like since the reservoir is like no memory and always in equilibrium.
Yeah.
I assume your system have like some quantum information in it, and it transfers to the equilibrium.
Right.
And where that information goes?
Very good. Okay. So like you might ask yourself, like you said, so I've started with some system in some phase state, and now I have like put it into the environment. Yeah. Okay. Where did that information go? It's basically being distributed among all the modes of the system very quickly, redistributed.
Okay.
So that what happens is that well, what do you mean by quantum information, right? That is a question you have to ask yourself. So you may say, well, maybe it's because of the phase. You know, there's a superposition between the system and the 0 and the 1 state, and now that phase relationship has been lost because it is now going into a phase relationship between all the modes of the environment.
Like for example, if like my system have one photon, and then one photon leak into the reservoir, into the environment.
Yeah.
But like now the reservoir will have one photon, right?
Yes.
Why do you think like it can be like you see the reservoir is still in the at the initial condition? Like why? Like I think the reservoir should have a photon in it.
Right, of course, the reservoir has a photon. We have to satisfy energy conservation of the system.
Yeah.
Okay, so that has not changed. Okay? But what has changed instead is the way in which this photon is distributed among all the modes of the environment.
Okay.
Right, so now the photon, originally the system was in some state, right?
Yeah.
Okay, and so I had some energy where the system was in, say, that energy. Okay, now this energy went into the environment, into some photon, but this photon could be in any 4 pi.
Okay.
Right?
Yes.
So I have not changed that part of it. I still have the energy in the system, in the total universe, but where the photon went, I don't know anymore, because it's in all 4 pi. So I've lost information about where the photon is located. Right? Okay. So that's what I mean by loss of the coherence or loss of the information. Good question, thank you. And finally, we have that bilinear coupling, which I'm going to now put down. Okay. What I mean by this is that HSR is of this form. Okay. S is a system operator that acts only on the system. R is a reservoir operator that acts only on the reservoir. And I'm saying that all of my coupling terms have this form, okay, which are bilinear. Okay? So no quadratics are allowed in this particular version of the master equation. Although there are generalizations for that also. Okay? Now, when I go to the interaction picture, remember, which is given by U, HSR, U inverse, right? You can decide how you want to distribute the time dependence. Remember, the U is going to be some e to the I, H plus HR, SR, HR, right? Times T, right? That was the U that I just erased over there. And you can decide how you're going to distribute these HS and HR. For example, you could make the time dependence go into S and time dependence go into R, because U has both HS and HR in it. So HS part will affect this guy, and R and HR part will affect that guy and make them time dependent. Okay? But usually what we'll do is we will make HSR such that we can put all the time dependence into the reservoir operator. Okay? Because it's just time dependence. I can move it around wherever I want, and I'll say that the new or the interaction picture operators are like this. And in fact, I'll drop this tilde over here just to make it easy. I should keep the tilde because these are all interaction picture versions, but I will just drop that because it's easier to write. So what I've done effectively is put all of the time dependence that was in this U into this part, the R dagger, and the R part of the Hamiltonian. Okay. So as an example, let's do the two-level atom interacting with the radiation. Okay, I'm erasing this, but it's already in your notes, so you can look back and look at this expression when I start doing the approximations. Okay. So, for example, for HSR, which is originally the coupling between the radiation field, sum over J, H bar dJ, AJ times 2, 1. So as you said, right, this is exactly the type of expression where energy is taken from the one state, or going from the two state to the one state, and a photon is destroyed in the environment. And similarly, the other term, which is the Hermitian conjugate, will contain that part where the system goes from the two to the one state and a photon is created in the environment. Here, the system goes from the one to the two state and a photon is destroyed in the environment. The other way, it goes in the other way. Okay? And as you can see now, the quantum information will go into many modes. So that's the problem. It's like an entropy increase of the environment. Okay? That's effectively what we are describing through this coupling between the Hamiltonian of the system and the environment. And now HSR till, remember the original HS, for example, HS would be H bar omega 2, right? That's the two-level atom, right? It just has a position, and HR is of course H bar, say nu J, AJ dagger AJ plus half, right? This was the original Hamiltonian for a two-level atom interacting with a radiation field, right? The HS is just the energy of the atom, HR is the energy of the electromagnetic modes. So now when I apply that interaction picture Hamiltonian, which is over here, I will get terms which go like this. So what I'm doing is I'm going to say H bar Gj times E to the I mu j minus omega t, okay, times Aj, okay, and then I'll get back my 2-1 matrix and the Hermitian conjugate. And I'm going to call this part over here as my FR of t. Okay? So this is the sort of the description of what is going on over here. I have essentially put it in this form here, which you are familiar with for the two-level atom interacting with the radiation field. You can immediately see exactly what those FR, those operators are. They are just simply the AJs which have been transformed into this rotating frames that are rotating at the frequencies of the electromagnetic field and the atom. Okay. So that carries all of the time dependence. Okay, and now, okay, the rest of this, in fact, I'm not going to try and go through it on the board because it just gets long and doesn't give you a lot of great insight. I'll just refer you to the notes and we'll just go through what's happening in the notes, okay? So if you look back at the terms in the master equation that I had written earlier, not the master equation, but the evolution of the system density operator, we had two terms in that, which one is called term 1 and term 2, as I have denoted in my notes. And as you can see, the first term in that first term in that evolution equation will have some term that has the expectation of the reservoir operator at time t equal to 0. Okay? And so usually what we do is we ignore this term 1 because all it does is it just modifies the behavior of rho s, looks like an extra term in the HS. So, for example, that what it will do is it will just modify slightly the frequencies of HS in this problem. Okay? And in fact, for the radiation field, it turns out, like in this case, in the radiation field, if it's in a vacuum state to begin with, then the expectation value for these operators, AJ, for example, in the vacuum state is always 0, right? So if you look at this guy, expectation in the vacuum state is 0, so we can just ignore it for the first term. Okay? So term 1 is always usually neglected. The term 2 is the one that we care about. And as you can see, it's a very complicated looking term. Okay? It has a lot of terms in it. And a typical term in that operator, in that evolution equation, is going to have a combination of system operators and these reservoir functions FR of t. Okay, so it's going to have many of these terms. In fact, it's always going to come in sort of this pairs, as you can see in the expression. So I'll just write down a typical term and we'll consider it. Okay. So So a typical term in this very beastly looking expansion, as I call it. It's a beastly thing because it's got so many terms and it looks very complicated. And we have to now bring in the assumptions or the approximations to simplify it. So a typical term in this expression will have the trace over the reservoir variables times s to the minus a fr of t to the power a, s to the minus b fr of t to the b, s to the minus b, rho r of 0 times rho s of t. T prime, sorry. Okay. And there's also an integral between 0 to t dt prime, which is sitting outside, but I'm just looking at what's inside that integral, which is over here. Okay. The a's and the b's represent, plus and minus, where plus is a dagger and minus means no dagger. Okay. And because this trace is over this product of these these density matrices, rho r of 0 and rho s of t prime, I can even write this as just this term fr of t to the a, fr of t to the b, rho r of 0. I guess I forgot a t prime over here. Sorry. Okay. 0. And then we have the term s minus b, s minus a, rho s of time t prime. Okay. And sometimes these could be on this side. Okay. It doesn't matter because in the end we are going, the way it was written, I just took one particular term, but there are terms where s minus a and s minus b could be on the other side of rho s. Okay. And this part over here, again, reminds you of these correlation functions. In fact, I define a correlation function GAB of T1, T2, which is indeed this expectation value, because the trace over the operators is simply the expectation value, as you remember, for these functions. So that's very nice because it means that we are going back to that understanding about two-time correlation functions between now purely the reservoir variables. Okay? We just have to worry about the reservoir variables over here, and we have to take their correlations at time t and t prime. Okay? And that's when we bring in the assumptions. Okay? And that's what I outlined. First assumption is equilibrium, or the Bond approximation that I mentioned earlier, Bond approximation, which says that the time t1 and t2 don't matter, it's just the difference in the times that matters. Okay? And the other is the Markovian, which means that there is no correlation away from t2, t1 equals t2. You can think of that as saying that these guys are delta functions. So when I look at the term in this notes that you see here, we had an integral over 0 to t dt prime of a typical term in this expansion. Okay, and what it's saying is, we don't need to look at what's going on at times all the way from 0 up to t for this expansion. We only need to look at what happened in the previous instant of time. Okay? And so in the next step, as you'll see, we in fact make this approximation, and we say that rho s of t prime is just equal to rho s of t in this expansion on the right hand side. Okay, so on the next page, if you look, you'll see that all of this has gone into rho s of t prime has become equated to rho s of t. So that was we don't need the full history from 0 up to t prime or the 0 up to t, the current time. Instead, we just use what happened at the time t to predict what will happen at time t plus delta t, which is what, in fact, if you look on the left hand side, we are carrying about the derivative of rho s of t. So we are only interested in what happens at time rho s of t to predict what is going on at rho s t plus delta t. We don't need to know everything about what happened all the way from 0 up to t to predict that value. And of course, you can relax this assumption. You can say, for example, oh, what will happen if we don't do that? We want to take into account maybe all of the previous history of the experiment all the way from 0 up to t, and there are in fact master equations which are non-local in time that will actually do those things, but most of what I describe, especially for say atom coupled to electromagnetic field, you can assume that this is relaxed, okay? Or you can assume that it is Markovian in this case. Okay, so the next term then has all of these terms, written out, and you begin to see now, if you look on the page, that you get terms like let's say the first term in the expansion over here. So a typical term in this Hamiltonian, sorry, not Hamiltonian, but in this expansion, let's say is 0 to t dt prime, and then I have g minus plus t prime. I think I'm looking at the second term in this expansion times s dagger s rho s minus s dagger rho s s. Okay, so you see all the information about the environment lives in this correlation function that I talked about earlier, and in fact we just have to evaluate this integral 0 to t prime dt prime of this environment, and everything about the system. These are the system operators at time t, for example. Okay, and this part is purely system operator. Okay, so if I go back, I just erased the Hamiltonian for the 2-level atom, but we just discussed it. The Hamiltonian for the 2-level atom, the coupling is just this Fr of t times S plus, where the Fr of t is summation over j, h bar, jg, aj, e to the I, omega minus mu j of t. Okay, that's this guy over here. And this guy S dagger is just 2-1, right? Okay, this is a 2-1 operator, so plus the Hermitian conjugate. Okay, so to evaluate what this term is, for example, I would want to write h, say plus minus of t comma t prime. We'll have the expectation of h bar squared summation over jk gj star, just expanding out all the terms. We'll have aj dagger ak e to the I mu j minus omega t and e to the minus I mu k minus omega t prime, expectation value in the state of the environment. Okay. And this is where actually you can put in different assumptions about the environmental initial state. So this is the trace over the reservoir, or the trace over, remember it's the trace at time t equal to 0, right, of the reservoir. Because the reservoir does not change its state over time. Okay. Normal assumption would be thermal equilibrium, right? You would say the system is in thermal equilibrium, so the reservoir has purely diagonal elements along its density matrix. Okay, and then of course this Aj and K. Okay, Then of course this expectation value for the so everything here is classical, right? I mean e to the I j nu j minus omega nu k minus omega. These are just some integrals that we'll have to do. The only quantum part comes in this operator over here, aj dagger ak, right? That's what we have to evaluate in given a certain state for the reservoir. The simple assumption is thermal equilibrium, but you could put in squeezed state, for example. This is another kind of interesting state that you could imagine that the reservoir was prepared. Okay, you could imagine this reservoir is prepared in a coherent state. Okay, whatever you want to put in, you can for the reservoir. This is where your understanding of the quantum properties of the reservoir can come in useful. Okay, but for example, squeezing. The reason I mentioned squeezing of the reservoir is this is actually an interesting current sort of topic, which is called reservoir engineering. Meaning, how do you engineer the quantum state of your environment to make the decay of your particle, of your atom, behave differently, okay, or the qubit behave differently. And this is called in reservoir engineering, dissipation engineering. There are various terms for it, but effectively it is sort of trying to prepare the reservoir in some interesting quantum state to create some different properties for the decay of the qubit that you are caring about. For example, if you have a squeezed reservoir, you can see when you squeeze a reservoir, you make the system more subject to decay along one direction than the other. Because when you squeeze, the uncertainty or the fluctuations in the reservoir in one direction are much smaller than the fluctuations in the other direction. Remember from the squeezing discussion that we did earlier. So for example, if you prepare the system not in a vacuum state or a thermal distribution, but you prepare the system, not the system, but the environment in a squeezed vacuum state. Now the fluctuations are more in one direction than the other direction, so you can understand that the coherence decay of the atom is going to be different in this direction versus that direction. So you can have unequal coherence decays for an atom which is prepared, which is interacting with a reservoir which is in a squeezed vacuum state. Okay? But to finish this story over here, yeah.
Sorry.
Yeah.
So when we talk about the reservoir engineering,
yeah.
about the squeezing the reservoir, I kind of understand maybe we can add another device to squeeze the vacuum noise.
Yeah. I didn't say how I'm going to do it.
I'm kind of curious, more general, how do we realize this reservoir engineering in the real experiment?
So that's a great question. Okay, so there are only a few cases that I know of where the reservoir engineering has been done experimentally.
Okay.
Okay, and there's a more general quantum information theory about all this. But the two examples I know, one is probably superconducting qubits, and the other is optomechanical systems.
Okay.
So where the mechanical system is interacting with some cavity, and also of course with the electromagnetic modes of the cavity. So you can have some device, like you said, which squeezes the vacuum state of the cavity, for example by engineering some nonlinear interaction, and that allows you to squeeze or prepare the mechanical oscillator in some different coherence state than the other, or make the decay of the mechanical oscillator different in one direction than the other, for example.
Yeah, for example, I read about theory paper about reservoir engineering talking about he want to make the reservoir from 3 mode become a 5 mode, this kind of.
So here you have the infinite modes.
Yeah.
Right. Typical squeezing, people will talk about 2-mode squeezing. Where you might have 2 frequencies which are around some central frequency of the qubit, for example.
Okay.
That would be a 2-mode squeezed vacuum. Okay. So, for example, an interaction or a you could have the squeezing operator. Well, maybe this is a great topic for your term paper. I don't want to go too much into the experimental details here. Okay, this is just an introduction to the topic. Okay. Yes, as you said, it's a very common, very interesting current research topic.
I see.
Yeah. So I can't cover all the things, but I think that would be great. Why don't you talk about squeezed reservoirs and stuff like that in your term paper, in your presentation. Okay, so to conclude the story then, I didn't, again, all the details are in your notes. This gives you expectation, AJ dagger, AK. which is just Nj delta Jk for thermal reservoir. For thermal reservoir. Okay? Where the Nj now will be exactly what you expect for a thermal reservoir, will follow the statistics for which are diagonal and will have the exponential distributions along the diagonal that you expect for a thermal reservoir. Okay? Okay. So when I put that in, into the expression G plus minus Pt prime, I get this h bar squared summation over j dj squared nj e to the I mu j minus omega t minus t prime. So we still have to carry out the sum over the modes of this function e to the I mu j minus omega. And also I should remind you there's an integral from 0 to t prime. So actually there's really all the time there is a 0 to t dt prime sitting in front of this. So we have to evaluate this integral 0 to t dt prime of this, but this is exactly what you have done many times already. We did it when we considered the transitions of multi-state systems, when we did from multi-state system bound to continuum transitions. We did it in Wigner-Weisskopf theory, and now we see it again over here. This is just simply going to give us some gamma, which is gamma is just as usual, just the sum 2 pi over the modes summation j dj squared no nj, but will give you delta of mu j minus omega. That's just the spontaneous emission rate for the electromagnetic field that we had put in. And so now the coefficient which has this nj in it will pick out the frequency omega for the term. So this guy will all get simplified to minus gamma over 2 n of omega. Okay? And if you do the other one, g minus plus e t prime, you'll find because for that guy instead of aj dagger ak, you'll get ak aj dagger. And for that one, you will now have to use the commutation relation. So you get aj dagger ak plus 1, right, for the commutation relation. So you end up for this guy with minus gamma over 2 n of omega plus 1. Okay. And all this results in the master equation for an atom interacting with the radiation field. E rho s, let me just write it on the other side because we're running out of space here. Again, remember that I have put in the assumption of thermal properties, but as I said, you can change those properties, you can make the reservoir have different properties, and you can derive a master equation for those situations. And this is the final sort of result, which is minus gamma over 2 n of omega times ss dagger rho s minus s dagger rho s. Remember, this is all an interaction picture, so I'll remind you by just putting the tilde back on this. Minus gamma over 2 n of omega plus 1 s dagger s rho s minus s rho s dagger plus Hermitian conjugates. Okay. This is in the interaction picture. If I go back to the Schrodinger picture, I have to add in those terms where the Hamiltonian for the system operators is involved. So the full guy will be written as all of that, okay, exactly all of those terms, okay, plus 1 over IH bar HS. So what we see is that by coupling the system to the environment, which is a radiation field, we get, say, the usual evolution due to any operators that are acting on the system. For example, so far we were assuming that operator might be just h bar omega, but you could have put in some driving term as well. Just like we studied earlier, we could have put in some classical laser field that is driving the system, and all that will go into HS, just like usual. And I will explain that in just a second. And then what we have derived is interaction with all of the modes, the vacuum modes of the electromagnetic field, gives you a decay term minus gamma over 2 n of omega minus gamma over 2 n of omega plus 1. And these have obvious physical interpretations that I want to discuss in a minute, but I just want to stop here and ask if there are any other questions about this before we go further. I mean, it's something that takes a little bit of study to follow all the mathematics, but I hope the physical picture of it is not so hard to understand. So now let's study what happens specifically for an atom which is being driven by some laser field while also undergoing these decay, and we'll immediately see some physical interpretation for these terms that we have just written down. Okay. So now, this is the topic that I call the optical block equations, which are very important. And that's because we can actually write down what that system operator is, S. We know that S is simply 2, 1. Okay. So we can substitute for that in those master equations. So this is the master equation again. I should have mentioned that. Which has been derived, as I said, in this Bond Markov Approximation. Okay. But by putting in that that S is equal to this 2, 1, and let's also assume that we have some HS equals minus H bar delta to 2. I've gone into the rotating wave approximation, which is interacting with some electromagnetic field, a laser in this case. Example, this is the classic situation that we are interested in. Then you can substitute, and I'm not going to carry out the math, it's in your notes, but we get 4 equations of motion for the population terms. The rho 2, 2, it goes as minus gamma n bar plus 1, rho 2, 2, plus gamma n bar rho 1, 1, and as I omega star, rho 2, rho 2, 1. Rho 1, 1 dot is equal to gamma n bar plus 1, rho 2, 2, gamma n bar plus 1. Then the coherence, rho 1, 2 dot, so that's minus gamma over 2, 2 n bar plus 1, rho 1, 2, minus I delta, rho 1, 2, plus I omega star over 2, rho 2, 2, minus rho 1. And this is the starting point for a lot of experiments or a lot of physics. There's also an equation for rho 2, 1, but since rho 2, 1 and rho 1, 2 are just related by complex conjugate, it's just obtained by complex conjugating this expression here. So a lot of experiments in atomic physics start out with these density matrix equations. So a lot of things like understanding everything from like experiments in optical susceptibility of atomic gas, you would start with these equations of motion, you would solve it for different situations. Maybe you have more than one laser field, maybe you have a 3-level atom, maybe you have 2 laser fields. All of that can come, you can easily be derived once you know the master equation, right? It's just a variation in the Hamiltonian HS and the size of the density matrix that you're considering, and the laser fields and so on can all be written down, and then you can understand the consequences of these equations by using some of the approximations. For example, one of the simple approximations would be, suppose delta is the largest frequency in the problem, okay? So for example, you have a laser which is far detuned from the 1-2 transition, then you can say if delta is the largest frequency in the problem, you can use adiabatic elimination. You can set ρ12 dot equal to 0, and you can express ρ22 and ρ11 in terms of omega and delta, and then you can substitute back here, you arrive at what we call the rate equations, okay? So that is the standard rate equation approximation, which comes from assuming that delta is the largest frequency, that is, it's adiabatically eliminated far-off resonant terms. So there are many approximations we can use, which I'm not going to have time in this course to talk to you about, but this is the starting point for those understanding of atomic physics that you can use these equations for. Okay? What is important also to understand is, you see that these omegas multiply ρ21 and ρ12 and cause changes in ρ22, right? Similarly, any difference in population between ρ22 and ρ11 causes a coherence to be developed between the 1 and the 2 states. So this is the coherent driving part of the master equation, which of course you would have found even without the decay terms, but now we can use the decay terms to understand the different regimes of decay. Okay? So you have coherent driving, which is proportional to omega for the processes in this master equation. Coherent driving, which is proportional to the omega, the Rabi frequency of the laser. Then you have stimulated excitation and emission, okay, by thermal phonons, because you can see here gamma in bar, right, causes ρ22 to decay, okay, which is proportional to the number of photons in the thermal reservoir. Okay, so that maybe kind of answers your question also a little bit about what are the different ways in which there is interaction of the photons between the reservoir and the atom. So what I'm saying is, I have the atom 1 and 2 in this case, right? Then there is a rate which goes from 2 to 1, which is gamma n bar, okay, which is driven by the reservoir. Okay, there is a corresponding absorption. It goes gamma n bar up from the state ρ11 up to the state ρ22, right? So they balance out in equilibrium, right? Plus we have an additional term, which is spontaneous emission gamma, which is the one over here. Okay. So in the absence of the coherent driving, these processes would establish equilibrium between the state 1 and the state 2. In fact, as you can see, that will be governed by the temperature of the bond, okay, and bond, right? So in steady state, for example, you could say set ρ22 equal to 0, or ρ22 dot and ρ11 dot equal to 0 in steady state, and you can obtain a ratio between ρ11 and ρ22, which will be governed by gamma n bar divided by gamma n bar plus 1, right? So that will be the way in which we can establish equilibrium conditions, which will be just returning back your equilibrium Boltzmann distribution between the state 1 and the state 2 for the atom. It's easy to see. You just set those to be 0. And so this is proportional to n bar gamma, Okay, stimulated excitation. Then there's spontaneous emission. So spontaneous emission, as you can see, goes only in one direction, which is proportional to gamma. Okay, so these are incoherent processes because, as you can see, they take population from 2 to 1 and 1 to 2 incoherently. Okay, this would happen irrespective of whether the system started with some coherence between 1 and 2 or whether there was just some population in 2 and some population in 1. And in vast majority of cases, there's no coherence. You just started with some distribution of population and then you see what happens. Okay, but you can also have decay of the coherence, as you can see from the third equation. The decay of the coherence ρ12 dot is going as minus, say, some gamma 12 ρ12, where gamma 12 is equal to gamma 1 plus gamma 2 divided by 2 is equal to 2n bar plus 1 times gamma over 2, seen over here. Okay. So the coherence decays at a rate which is gamma over 2 times 2n bar plus 1. And of course, in many situations, for example, at optical frequencies, right? Optical frequencies are in the electron volt regime, right? Let's say 1 or 2 electron volts, and room temperature is on the order of 25 milli electron volts. So therefore, for an atom, optical situation, an atom, the n bar is pretty much close to 0 in most situations for atoms that are interacting with optical field. Now, if you have a superconducting qubit, then that may not be true because the superconducting qubit frequency is on the order of gigahertz, which is on the order of micro eV rather than milli eV, and so at room temperature, a superconducting qubit, the n bar is going to be extremely high, which is why we have to cool down the entire system if you want this superconducting qubit to see a nearly zero temperature environment. Okay, but you can solve the problem also for situations where the environment is non-zero using this fact that n bar plus 1 affects the rate of decay of the system. Okay, I have to stop here. So in the next class, I'm pretty much going, so let me finish by just saying that if you look at your notes, you'll see that I also made some more remarks about the master equation and its derivation, where I've examined in more detail this Bond and Markov approximation. So if you're interested, you can read that to understand in why we have to make 2 approximations, or is even just 1 approximation good enough. Okay, and in fact, you'll see in most situations where you make the Bond approximation, the Markov approximation will automatically be true. Okay, of course you can insist, no, I don't want to make the Markov approximation, I just want to use the Bond approximation. But this last bit that I have put in this notes here examines when Bond and Markov approximation work together, and usually it turns out that they both are valid. In most common situations, if the Bond approximation is valid, the Markov approximation will also be valid, so it makes sense to do them both together. Okay? Alright, I'm going to stop here. In the next class, we'll consider quantum information processing. This sort of brings to an end sort of the open quantum systems part of the class, or the quantum optics part. Yes?